A roar comes downriver. The volunteer runs. Behind it, boulders knocking together, trees snapping at the trunk, a creek turning into moving concrete. That is Mount Rainier, 14,410 feet of rock wrapped in a cubic mile of ice, 60 miles from Seattle. The easy answer is that a volcano plus glaciers makes mud. The correction is worse. The flat ground under Orting was delivered by a flow that needed no eruption, and flows like it arrive every 500 to 1,000 years. Why does the mountain's worst hazard aim at the towns built on top of the last one? The date was August 13, 2015, and the volunteer was working in the Tahoma Creek drainage on the southwest side of Mount Rainier National Park, in a valley most visitors drive past without ever learning its name. At roughly 9:40 in the morning, about half an acre of the terminus of the South Tahoma Glacier broke away and released water that had been stored inside the ice. There was no earthquake anyone felt, no ash, no smoke. What the volunteer had to work with was sound, and the sound arrived before anything else, a low roar coming down the valley. Then the specific percussive noise of rocks the size of cars striking each other underwater, then trees breaking, not falling, breaking at the trunk one after another, which is what happens when a wall of saturated debris hits standing timber at the base. The volunteer moved to higher ground. That is the entire survival strategy, and it worked, because at Tahoma Creek, there is high ground within a short sprint, and the valley walls are close. A second volunteer stationed up at Indian Henry's hunting ground heard the same signal, understood what it meant, and repositioned near the suspension bridge to watch the surges come through. That detail matters more than it looks. Two people with no instruments, no alarm, no phone call, correctly identified a debris flow from acoustics alone and put themselves somewhere it could not reach. Everyone in the park that day was accounted for by evening. The seismic station on Emerald Ridge, which does have instruments, logged what the ears had already reported. 4 distinct events, 9:40 a.m., 10:30, 11:30, and 12:40 in the afternoon. The strongest was the 11:30 pulse, and the debris flow it generated reached the West Side Road at about noon. Roughly 7 separate waves came down through the rest of the day and into the evening. The road took damage and closed. The park spent the following days walking the trails to see what was left of them. That is what a small one looks like. Half an acre of ice, an afternoon of surges, 1 closed gravel road, 0 fatalities. Hold that image, because everything in this story scales from it, and the scaling is not gentle. Now move about 25 miles northwest down out of the park, to a town called Orting. Orting sits on a flat triangle of ground, where the Carbon River joins the Puyallup. Several thousand people live there. It has a downtown, a high school, an elementary school, farms on the valley floor, and one of the more pleasant views of the mountain in western Washington, which is a large part of why people move there. The valley floor is remarkably level. Farmers like it for that reason. Developers like it for that reason. Anybody who has ever poured a foundation likes it for that reason. That flatness is not a coincidence of erosion. It is a deposit. The ground under Orting was laid down by a single event that came off Mount Rainier and filled the valley, and the tree ring work that dates it puts that event in the year 1507, most likely in late summer. Geologists call it the electron mud flow, after a small community upstream. It buried the Puyallup Valley in a slurry of rock, mud, ice, and shredded forest more than 26 feet deep at its thickest point, and it ran something like 34 miles from the mountain. When you stand in downtown Orting, you are standing on it. On the first Monday of every month at noon, sirens mounted on poles from Orting all the way down to the port of Tacoma sound for a couple of minutes. People eat lunch through it. Kids in the schools have heard it their entire lives. Once a year, the school district runs the drill for real, and the students walk their evacuation route out of the valley on foot. Because in Orting, the plan is not to drive. Driving is the plan that fails first. There are a handful of road bridges out of the valley floor. all of them low, all of them inside the zone the flow would occupy, and a few thousand vehicles trying to use them at once is not an evacuation. It is a parking lot with a deadline. So the city is building a bridge for pedestrians. It runs from the Foothills Trail, crosses State Route 162, and climbs toward the higher ground on Rocky Road Northeast, with a second span planned to carry people over the Carbon River and up the hill toward the plateau at Tejale. It is 20 to 30 feet wide. The design target is to move about 12,000 people to safety in 30 minutes. The price tag runs to roughly $9 million, and it is a bridge that goes essentially nowhere on an ordinary Tuesday. It exists because the modeled warning window for Orting is about 40 minutes, and because the difference between 40 minutes and 30 minutes is the difference between a town that gets out and a town that doesn't. That is a strange thing to build. Think about what it implies. Not a levee, not a dam, not a diversion channel, not a wall. Nobody has proposed stopping the thing. The entire public investment is aimed at helping people walk uphill fast enough. That is a statement about the size of what is coming, and the honesty of it is unusual in hazard planning. To understand why the engineering gave up on blocking it, you have to look at the mountain the way the mountain is actually built, which is nothing like the postcard. Mount Rainier stands 14,410 feet above sea level, and that number by itself is misleading because altitude is not the hazard. Relief is. The mountain rises out of a lowland that sits barely above sea level, so the vertical drop from summit to valley floor is close to the full 14,000 feet, and it happens over a horizontal distance of only 15 to 20 miles. That is a ramp. Anything that comes loose up high arrives with an energy budget set by that drop, and the rivers that drain the mountain have spent the whole Holocene carving efficient, steep-walled, straight-running channels that funnel material toward the Puget lowland with very little friction to waste. On top of that ramp sits the ice. Rainier carries roughly 24 major glaciers, plus a scatter of unnamed snowfields and permanent snow patches, covering about 36 square miles, close to a tenth of the national park. The total volume is around 1 cubic mile. That is more snow and ice than all the other Cascade volcanoes combined, several times over. The Carbon Glacier on the north side has the lowest terminus of any glacier in the contiguous United States, its snout ending down at about 3,600 feet in dense forest, and it is the thickest measured ice in the lower 48 at roughly 700 feet. The Emmons Glacier on the east flank covers the largest area, better than 4 square miles. A cubic mile of ice is an abstraction. Convert it. Ice is water that has been temporarily immobilized on a slope at an elevation where it does not belong. And every ton of it is potential energy plus potential fluid. Rock alone tends to stop. Rock plus water travels. The single most important physical fact about Mount Rainier is that its slopes come preloaded with the exact ingredient that turns a landslide into something that behaves like a liquid and refuses to stop until it reaches sea level. The mountain drains through 5 main river systems, and each one is a delivery route with a name and a mailing address. The Puyallup and the Carbon run west and northwest and merge before reaching Tacoma. The White River runs northeast, then swings north toward Auburn and Kent and the Green River Valley. The Nisqually runs southwest toward the town of National and on toward the delta at the south end of Puget Sound. The Cowlitz drains the southeast side toward the Columbia. Those valleys are not random. They are exactly where the mountain has sent material before, and they are graded and smoothed by the last few flows, which is why they are attractive places to build a road. So people built roads in them. State Route 706 runs up the Nisqually Valley to Longmire and on to Paradise. State Route 410 climbs the White River drainage toward Chinook Pass and Crystal Mountain. State Route 165 runs south from Buckley through Wilkson and Carbonado to the Carbon River entrance. State Route 162 runs the length of the Puyallup Valley through Orting. Rail lines took the same corridors before the highways did, for the same reason. The grades are gentle, and the ground is already flat, which produces the geometry that defines everything that follows. In every valley that drains Mount Rainier, the evacuation route and the inundation zone are the same piece of ground. There is no parallel road on the terrace above. If a flow is coming down the Puyallup, the highway that would carry you out of the Puyallup is in the Puyallup. Your options are to go up the valley wall on foot or to be in the flow. So here's the question the rest of this story is built on. What actually makes 14,000 feet of volcano let go? Start with the obvious answer, because it is half right. An eruption pushes heat into a mountain that is wearing a cubic mile of ice. Hot rock meets snow. Snow becomes water in seconds rather than months, and the water has nowhere to go but downhill through loose volcanic debris. The USGS description of the resulting flow is deliberately unglamorous. It looks and behaves like flowing concrete. That is not a figure of speech chosen for drama. It is a description of the physics. Ordinary floodwater is water with some sediment in it. A lahar is sediment with some water in it, and the ratio changes everything. Once the solid fraction gets high enough, the mixture stops behaving like a river and starts behaving like wet cement being poured out of a truck. It has strength. It can carry boulders the size of delivery vans in suspension, not rolling along the bottom, but floating in the body of the flow, because the fluid around them is dense enough to hold them up. It does not spread out and thin into harmlessness the way a flood does on a floodplain. It holds together, holds its depth, and keeps going. It also grows as it moves. This is the part people underestimate. A flow that starts as a landslide of a certain size scrapes up everything it crosses: snowpack, glacier ice, riverbed gravel, soil, standing forest. Geologists call it bulking. A flow can leave the mountain at one volume and arrive in the lowland at several times that volume, having eaten the valley on the way down. The trees are not obstacles. They are fuel for the mixture. The mixture snapped off and ground into the slurry, which is why the deposits are full of shredded wood and why buried logs are the reason we can date these events at all. Then there is the shape of the channel. Water spreading across an open plain loses depth and loses speed. A dense flow squeezed into a steep-walled river valley does the opposite. Confinement keeps the mass together, keeps it deep, and depth is what preserves velocity. A valley that narrows can pile the flow higher, and when it comes out of the constriction, it comes out fast. The valleys around Rainier are narrow where they leave the mountain, and only open up near the towns, which means the towns receive the flow after the terrain has finished accelerating it, and when it stops, it sets. Water drains out of the deposit, the sediment locks together, and what was liquid becomes a firm gray plain that supports a plow, a rail line, a school. That is the trick of the whole system. The evidence of the last catastrophe is indistinguishable from good real estate. So an eruption melts ice. The melt mobilizes debris, and the valleys deliver it. Clean chain. Easy to teach in a classroom. It is also the reason the hazard was underestimated for most of the 20th century, because it contains a comforting implication. Eruptions announce themselves. Magma moving into a volcano produces earthquakes, ground swelling, gas emissions, changes in the hot springs. Give a modern monitoring network a volcano that is waking up, and it will tell you weeks or months in advance. If lahars require eruptions, then lahars are a solvable problem. The problem is that the largest flows in Rainier's recent geologic history were not, at their core, melting events. They were structural failures. The mountain fell down. To see why, look at what magmatic heat does to a volcano when there is no eruption at all. Under Mount Rainier, there is a system of circulating water. Rain and meltwater sink into the fractured pile, get heated at depth, pick up volcanic gases, and come back up as acidic, mineral-charged fluid. The evidence for it is on the surface right now. Warm ground at the summit that keeps ice caves open inside the crater rim, steaming vents, mineral springs on the flanks. The USGS operates hydrothermal monitoring sites on the mountain for exactly this reason. It is not dormant plumbing, it is running. What that fluid does to rock is the single most important process in this entire story, and it happens invisibly inside the mountain over centuries. Fresh volcanic rock, andesite, is hard and strong. Run hot, acidic water through it for long enough, and the minerals begin to break down and reassemble into clay. Not clay in the pottery sense necessarily, but clay minerals. Soft, slippery, water-absorbing, mechanically weak. The reactions replace much of the original rock with material that has almost no strength when it is saturated. And it stays saturated because it is buried in the wettest volcano in the Cascades. Strong rock becomes weak rock in place, holding its shape, keeping its position on the slope, looking exactly like the mountain it used to be. The geologist David Montgomery put it about as bluntly as anyone has. Mount Rainier is a big pile of rotten volcanic rock with an ice cube on top. That is not a slogan. It is a mapped condition. Surveys of the mountain, including magnetic and electromagnetic data that can see through surface cover, indicate appreciable thicknesses of hydrothermally altered rock sitting high on the volcano, particularly west of the modern summit in the region of the Sunset Amphitheater. The Sunset Amphitheater is a huge bowl gouged out of the upper west flank, and its walls expose the altered material directly, streaked yellow, orange, and rust-red rock, the colors of iron and sulfur reactions, standing at high angle above the head of the Puyallup drainage. Fractures caused by the downslope creep of that altered mass have been documented there. The rock is not waiting to be weakened. It has already been weakened, and it is already moving, slowly, in the direction the map says it would go. Now put the ingredients together. Take a large volume of clay-rich, water-saturated, mechanically weak material. Place it at 14,000 feet, high on steep slopes, where its own weight is pressing it downhill. Add the freeze-thaw cycle of a subarctic climate at altitude. Add the loading of seasonal snowpack. Add the constant vibration of a seismically active region. And add the fact that the fluid, which produced the weakness, is still circulating and still producing more of it. Sizable flank collapse at Mount Rainier is not a random event that requires a special cause. Studies of the volcano describe it as promoted by exactly this combination: voluminous, weak, hydrothermally altered rock situated high on steep slopes. The mountain manufactures its own failure surface. What it lacks is a schedule, which is where the comforting version of the story falls apart. If the collapse is driven by alteration rather than by magma, then the trigger can be almost anything, and some of the candidates produce no warning signs whatsoever. A regional earthquake, a steam explosion in the hydrothermal system, an unusually wet season raising pore pressure inside the altered mass until friction loses the argument with gravity, or nothing identifiable at all, simply the last increment of weakening in a process that has been running for centuries. And there is a second consequence that is easy to miss and impossible to unsee once you have it. Clay is not just weak. Clay is the ingredient that makes a debris flow travel. A landslide of clean, dry rock breaks apart, loses its water, and stops, usually within a few miles. A landslide loaded with clay and pore water behaves like a cohesive fluid. The clay holds the water inside the mixture instead of letting it drain away, which keeps the flow lubricated for hours instead of minutes, which is why cohesive lahars are the ones that reach the sea. The same chemical process that removes the mountain's strength also converts the resulting debris into the long-distance version of the hazard. That is the machine. Heat makes acid water. Acid water makes clay. Clay makes both the failure and the fluid. and the valleys make the delivery. No eruption required at any step. It sounds like a theoretical worry until you go looking for it in the ground. The Puget Lowland keeps a very good record. Every one of these flows left a distinctive layer, and the layers are stacked, and they are dated, and the towns are built on them. The largest of them has a name that comes from a small settlement in the White River Valley, and it is the one that rearranged the geography of an entire region. About 5,600 years ago, Mount Rainier was a taller mountain than it is now. Then the top of it came off. The event is called the Osceola Mud Flow, and the work that pinned down its behavior is a study by James Vallance and Kevin Scott, published in the Geological Society of America Bulletin, which reads like an autopsy performed on a landscape. Their volume figure is 3.8 cubic kilometers. To make that mean something, the whole ice cover of the mountain today is about 1 cubic mile, roughly 4 cubic kilometers. Osceola was comparable in bulk to every glacier on Rainier moving at once, as mud. It began as a water-saturated avalanche off the summit and the northeast flank during small phreatomagmatic eruptions, the kind produced when magma meets groundwater and flashes it to steam. That is the piece the comforting version of the story likes to hold on to. There was volcanic activity involved. Look at what the eruptions actually did, though. They did not blast the mountain apart in the way St. Helens would in 1980. They destabilized a mass of rock that had already been converted to clay by hydrothermal alteration, and the mass did the rest. What came down was not lava and not ash. It was the mountain's own rotted upper kilometer, wet through. The scar is still there. The failure removed enough of the summit region to leave a horseshoe-shaped crater about 1.8 kilometers across, open to the northeast. The modern summit, with its 2 craters and its ice caves, was built afterward, filling the hole with new eruptions over the following centuries. When you look at Mount Rainier today, you are looking at a repaired mountain. The transformation happened almost immediately. Vallance and Scott found that the mass converted completely from a debris avalanche into a clay-rich, cohesive lahar within 2 kilometers of its source. 2 kilometers. From the summit, that is less than the distance to the top of the Emmons Glacier. There was no phase where anyone downstream could have watched a slow-moving landslide and made plans. By the time the material had dropped a fraction of its total elevation, it was already a fluid, and it was already moving. The reason it transformed so fast is the reason that matters for the future. The pre-avalanche mass already contained large volumes of pore water and abundant weak hydrothermally altered rock. The failure did not have to find water. It brought its own. Then it went down the White River. It filled the valleys of the White River system north and northeast of the mountain to depths of more than 100 meters. Not 100 meters at the deepest point in a narrow gorge. More than 100 meters through the valley system. Put a 30-story building in that valley, and the flow goes over the roof. Downstream, 40 to 50 kilometers from the volcano, the flow ran into a constriction in the valley and hydraulically dammed behind it, backing up and building depth, then discharging through the gap. At that location, Vallance and Scott estimate a velocity of about 19 meters per second and a peak discharge of roughly 2.5 million cubic meters per second. Numbers that large stop registering, so translate them. 19 meters per second is about 42 miles an hour, 30 miles from the mountain, in a mixture with the density of wet concrete, carrying boulders and whole trees. There is no running from that and no driving from that on valley floor roads. As for the discharge, the Amazon River delivers something on the order of 200,000 cubic meters per second at its mouth in flood. This was 10 times the Amazon for the minutes it lasted, made of mud, coming out of a single valley in Washington state. It did not stop at the mountain front, which is what makes Osceola different from a large landslide. It flowed north and west for more than 120 kilometers total, covered more than 200 square kilometers of the Puget Sound lowland, and ran out into Puget Sound itself. USGS mapping of the deposits, counting the full extent of related material, puts the covered area at around 550 square kilometers. The deposits reach the sites of present-day Auburn, Kent, and Commencement Bay in Tacoma. Near Sumner and out on the Auburn and Puyallup deltas, the mudflow layer is 20 to 30 meters deep. Read that list of place names again because it is a list of exits off Interstate 5 and State Route 167, and a list of school districts, warehouses, and light industrial parks that employ hundreds of thousands of people. The Osceola mudflow filled the Duwamish and Puyallup arms of Puget Sound. Before it arrived, salt water reached much further inland than it does today. The flat agricultural and industrial corridor that runs from Tacoma up toward Renton exists in its present form because a volcano poured 3.8 cubic kilometers of itself into a marine inlet and turned it into land. The port of Tacoma sits on the delta that grew out of that sediment. The Enumclaw Plain, that broad shelf of level ground that makes the drive from Auburn to Enumclaw so oddly flat for a place, at the edge of the Cascades, is Osceola. A formerly rugged, hilly landscape was buried under hundreds of feet of volcanic mud and came out smooth. Something over 500,000 people now live on that plain and the ground it created. Here is the part that changes how you read every farm and cul-de-sac in the valley. The flatland was not chosen despite the mudflow. It was chosen because of the mudflow. Level ground with deep, well-drained, fertile, volcanic soil. No boulders to clear. Gentle grades for rail and road. Room to build on a scale the surrounding hill country does not offer. Every quality that made those valleys attractive to farmers in the 1870s and to logistics companies in the 2020s was manufactured in a few hours by the hazard itself. The deposit is the advertisement, and people were there for it. Archaeologists working near Enumclaw have found evidence of human encampments buried beneath 75 feet of Osceola mud. There is no way to know what those people saw or how much time they had, and no responsible account should pretend otherwise. What the stratigraphy establishes is only this: the valley was occupied, and then it was under 75 feet of the mountain. Osceola is not alone in the record, and the other entries matter because each one demonstrates a different pathway to the same result. Before Osceola, sometime prior to 5,600 years ago, the Paradise and Reflection Lakes lahars came off the mountain as avalanches of hydrothermally altered rock and ran at least 38 kilometers down to the site of National, in the Nisqually Valley. The colorful, chemically cooked rocks in those deposits are visible near the Paradise Visitor Center, where several 100,000 people a year eat their lunch on top of them without knowing what they're looking at. About 2,500 to 2,600 years ago came the Round Pass mudflow, and this one is worth holding on to because of where it started. It began as a sector collapse of hydrothermally altered rock from the Sunset Amphitheater and the Tahoma Glacier headwall on the west flank. It went at least 30 kilometers down the Puyallup drainage, was Omal de Puyallup trails, and it also sent material down the Nisqually side toward National. Its deposits reach as much as 300 meters above the valley bottoms in places and run up to 30 meters thick in the valleys themselves. 300 meters above the valley floor means the flow was not filling the valley. It was climbing the walls, banking on the outside of bends the way a car does on a racetrack, because it was moving fast enough that the corners could not turn it. Then, 2,200 to 2,300 years ago, the National Lahar, produced by an explosive eruption that scattered a distinctive ash layer across the region. Hot rock mixed energetically with snow and ice, and the resulting flow traveled at least 100 kilometers down the Nisqually Valley. That one is the textbook case. Eruption first, Lahar second, exactly the way people assume it works. Add them up and a pattern falls out that is more uncomfortable than any single event. Some of these flows were caused by eruptions. Some were caused by the collapse of rock that had been quietly rotting for centuries. The lowland deposits look broadly similar either way. The towns are on all of them. and the recurrence interval for major lahars at Mount Rainier, across the last several thousand years, runs somewhere between 500 and 1,000 years, with smaller flows far more often than that. That forces a question the Osceola story cannot answer on its own. Osceola had eruptions attached to it, small ones, but real. If every big collapse comes with volcanic activity, then a modern monitoring network still has a chance to see it coming. So what does one look like when there is nothing to see? In the late summer of 1507, the west flank of Mount Rainier let go. Nobody in Europe had heard of the place. Columbus had been dead a year. In the Puyallup Valley, a forest of mature Douglas fir was standing in bottomland that had been forest for centuries. And then it was not, because a mass of hydrothermally altered rock came off the high west side of the volcano, in the neighborhood of the summit and the Sunset Amphitheater, and became a lahar. It ran about 34 miles down the Puyallup, covering roughly 13 square miles of the valley, more than 26 feet deep at its thickest. It reached at least as far as the site of Sumner. It laid down the ground that Orting now sits on, and it did it in a matter of hours. What it did not do is the whole point. It left no ash. That absence is the most consequential negative result in Cascade volcano hazard science. When a volcano erupts, it deposits tephra, and tephra layers are durable, mappable, and datable. Researchers looking at the electron deposit have not found an eruptive layer that matches it. The USGS position is stated flatly and without hedging in the wrong direction. There is no evidence indicating whether an eruption or some other event triggered the lahar, and no evidence of eruptive activity associated with it. The flow was caused by a large landslide off the west flank. The trigger remains unknown and genuinely disputed. Candidates include a hydrothermal steam explosion, an earthquake, or simple saturation-driven failure of the altered mass. And the honest scientific answer at present is that nobody knows. The date itself is a piece of detective work worth understanding, because it is how the summer timing was established, and the season is a clue. Radiocarbon dating on the trees killed by the flow put the event around 1500, which is close, but not close enough to distinguish between possible causes. So researchers went to the wood itself. Douglas firs buried standing in the deposit preserved their rings, and the outermost ring under the bark records the last season of growth before the tree died. By matching the ring width patterns of those buried trees against long, precisely dated ring records from ancient trees on Vancouver Island, a technique known as wiggle matching, the geologist Patrick Pringle and colleagues aligned the dead trees to the living calendar and produced a date, 1507, with the trees killed in late summer, after that year's growth ring had substantially formed. Pringle's own framing of why this matters is disarmingly modest. Knowing the seasonality of the electron mud flow, that it happened in summer, helps figure out what it isn't. In the Cascades, the enormous rain-driven floods come in autumn and winter, when atmospheric rivers park over the range and drop 1.5 feet of water in a day and a half. A late summer failure is not a rainstorm event. It is the driest, most stable part of the year, the time when a valley is at its safest by every intuitive measure, and the mountain came down anyway. Sit with what that means for anyone downstream. There was no storm to watch, no earthquake anyone has been able to identify in the record. No eruption, no ash on the snow, no plume visible from Commencement Bay, no rumble to make people look up. A slope failed, and a valley that had been forested for centuries was under 30 feet of mud. And the only warning that reached anyone would have been the same one the volunteer got at Tahoma Creek in 2015. A sound, arriving with a few minutes of lead at best. This is the reversal that governs the modern era. Warning depends on a sign. An electron proves the sign may never appear. Every monitoring instrument built for volcanoes is designed around magma. Seismometers listen for the small, characteristic earthquakes that swarm as magma cracks its way upward. tilt meters and GPS receivers measure the ground swelling as a reservoir inflates. Gas sensors watch for sulfur dioxide, which is the signature of magma close enough to the surface for its dissolved gas to escape. Those instruments are excellent. They work. They have given weeks of notice at volcanoes around the world, and at Mount St. Helens in 1980 they gave 2 months. Point that entire toolkit at a slope that is failing because of chemistry rather than magma, and it goes quiet. There is no reservoir inflating, because no new magma is moving. There is little to no sulfur dioxide, because the heat source is deep and old. The altered mass creeps down slope by centimeters a year, which is measurable if you happen to have instruments on that exact patch of rock, and if you know what threshold means failure, and nobody knows what that threshold is. Rainier gave the Puyallup Valley a full-scale demonstration of the no-notice lahar in 1507, and 5 centuries of instrument development has not solved the problem it posed. It has only clarified it, which redirects the entire strategy. Because if you cannot predict the failure, the only remaining variable you can influence is the time between the flow starting and the people moving. That shifts the question from the summit to the valley, and from geology to a stopwatch. But before the stopwatch, there is a longer human question, and it has been answered by people who lived here for thousands of years before anyone built a siren. The mountain has many names, and the names are not decorative. In Lushootseed, the language of the Puyallup, the Nisqually, and their neighbors, the mountain is Tahoma or Tacoma, from roots carrying the sense of snowy mountain and, in the interpretation carried by the Puyallup tribe, Mother of Waters. A Puyallup tribal language consultant, Dr. Zalmai Zahir, has published the first comprehensive analysis of the many native names for the mountain and the metaphors embedded in them. Mother of Waters is a causal statement. It says in 3 words that the rivers of this region are the mountain, in liquid form, arriving where you live. Everything that comes down the White, the Puyallup, the Carbon, and the Nisqually came off that peak. The water did. The gravel did. The fish runs are governed by it. And the mud did too. The land now administered as Mount Rainier National Park has been, since time immemorial, the ancestral homeland of Cowlitz, Muckleshoot, Nisqually, Puyallup, Squaxin Island, Yakima, and other Coast Salish peoples. They hunted mountain goat on the flanks, gathered huckleberries in the subalpine meadows in late summer, took cedar bark for baskets and regalia, and fished the cold, clean water that the mountain produced. Their relationship with the peak was seasonal, mobile, and detailed, which is a different thing entirely from either avoiding it or ignoring it. Oral traditions of the Nisqually and Puyallup describe the mountain as an actor with a history, a peak with a story of arrival and conflict, not an inert backdrop. It would be easy and dishonest to claim from that a fully articulated pre-instrumental hazard map. What can be said accurately is narrower and still striking. The people who lived longest with this mountain named it for the water it sends downhill, described it as something with agency and a record of behavior, and organized their lives around a seasonal round in which the high country was used at the times of year it could be used, and the settlements sat where they made sense for fishing, trade, and travel. The knowledge system was continuous observation across generations, held in language and story rather than in instruments, and it was the only warning system that existed here for several thousand years. Then came a different way of using the same valleys, and its central feature was that it did not move with the seasons. It stayed, it built, and it required the ground to hold still. In 1865, the Meeker family planted hops in the Puyallup Valley. Hops are a demanding crop that reward deep, rich, well-drained soil and level ground, and the valley floor delivered both, for the reason we have already established. The crop made money on a scale that reorganized the region. Growers got wealthy, Tacoma developed into an export center on the strength of it, and the valley filled with hop yards, drying kilns, and the seasonal labor camps that went with them. Hop growing in the valley ended abruptly in the 1890s, killed by aphids and mildew rather than by anything geological, and the farms shifted to berries, bulbs, dairy, and vegetables. The pattern was set. The flat ground paid. Coal did the rest. Wilson shipped its first load to Tacoma in 1877, and the mines at Carbonado went into production in 1880, both of them in the Carbon River drainage, upstream of Ording. Pierce County coal mining peaked between 1880 and 1900. Getting coal out of a mountain valley requires rail, and rail requires grade, and the only gentle grades available run along the rivers. Northern Pacific built line from Tacoma, up through Puyallup, through Orting, and on to Wilson and Carbonado, and in 1887 completed its crossing of the Cascades at Stampede Pass, with the main line running down through Orting and the Puyallup Valley into Tacoma. So within about 25 years of the first American farms, the valley floor built by the electron mud flow held farms, towns, a railroad main line, and the transport corridor for an entire coal field. Nobody made a reckless decision. Every individual choice was rational, and the accumulation of rational choices produced a population concentrated in the one place on the map that Mount Rainier reliably visits. Timber followed the same logic and added its own. Mills went where the logs could be floated or railed, which meant the river valleys, and logging pushed further up the drainages toward the park boundary through the early 20th century. Mount Rainier National Park was established in 1899, the fifth national park in the country, and the tourist road up the Nisqually reached Longmire and then climbed toward Paradise, hauling automobiles full of visitors into the same valley that the National Lahar had run 100 kilometers down. The mountain became a destination for climbers at the same time. Guiding operations formed around the Paradise side, and by the middle of the century, thousands of people a year were attempting the summit, most of them by the Disappointment Cleaver route on the southeast flank which crosses the Ingraham Glacier. Hold that name. It comes back. By the second half of the 20th century, the exposure had changed character entirely. The valleys were no longer farm country with a railroad. They were commuter corridors for the Seattle-Tacoma metropolitan area, with subdivisions on the valley floor, schools sited for the population they served, and a highway network that follows the rivers because the rivers are the only flat routes. Sumner and Puyallup together hold more than 50,000 people. Estimates of the total population living inside mapped Rainier-Lahar inundation zones run from roughly 80,000 to well over 100,000, depending on which zones and which time of day you count. And the daytime number is higher than the residential one because of the warehouses, ports, and industrial parks built on the Osceola and Electron deposits. That is the context for the number that ranks Mount Rainier against every other volcano in the United States. In the 2018 National Volcanic Threat Assessment, the USGS scored American volcanoes by combining hazard factors with exposure factors. Kilauea ranked first, Mount St. Helens second, Mount Rainier third, with an overall threat score of 200. 3. Rainier does not have the eruption frequency of Kilauea or the recent violence of St. Helens. What it has is the largest number of people living in mapped volcanic debris, flow hazard zones of any volcano in the country. It is worth stating that precisely because the loose version of the claim is wrong and the accurate version is worse. Mount Rainier is not America's deadliest volcano by body count. That distinction belongs to Mount St. Helens, which killed 57 people on May 18, 1980, in a lateral blast preceded by weeks of earthquakes, visible bulging of the north flank, and a national media circus. Rainier has killed people, and this story will get to them, but not on that scale, and not in that way, not in recorded history. The USGS assessment of Rainier is a forward-looking one, and it is more disturbing than a historical death toll, because it describes an event that has already happened repeatedly. has left its deposits under a metropolitan area, requires no eruption, and would give a modern city minutes rather than months. There is a habit of thinking that goes with living somewhere like that, and it is not stupidity. Ording has an annual drill and monthly sirens, and the town keeps growing. The reasoning is straightforward. The recurrence interval is measured in centuries. The ground is flat and fertile and close to jobs, and the alternative is to abandon some of the best connected land in western Washington on the strength of a probability nobody can put a date on. Every person in that valley is making a bet that most of them will win. The system only has to work once to make the bet look insane in retrospect. And until then, it looks like a reasonable place to raise a family, which it also is. And the framing so far has been too narrow anyway, because it treats Mount Rainier as a hazard that lives in river valleys and threatens people who chose to live in them. That is not the full inventory. The mountain kills people who never enter a valley at all, and it does it through mechanisms that have nothing to do with lahars. And the first large-scale demonstration of that came out of a cloud on a December day at 9,000 feet, carrying 32 men who never saw the mountain they hit. On December 10, 1946, 6 Curtiss R-5C commando transports left Southern California for Seattle. The R-5C was the Marine Corps version of the C-46, a big twin-engine hauler that had spent the war flying supplies over the Himalayas. And this was a routine peacetime movement of personnel. More than 200 Marines heading north, distributed across the 6 aircraft. Aircraft number 39528 carried 32 men. The objective was ordinary: get people from one base to another before Christmas. The conditions at departure were manageable. The aircraft were airworthy. The crews were experienced. And the route was flown constantly. Weather over southwestern Washington was heavy, so the formation flew on instruments at 9,000 feet. Stop there and consider what 9,000 feet meant in December 1946. It meant the aircraft were inside cloud with no visual reference, using the navigation technology of the era. Magnetic compass, airspeed indicator, clock, and the low-frequency radio range, a system that broadcast interlocking Morse signals so a pilot could hear whether he was left of course, right of course, or centered. There was no ground radar watching civilian and transport traffic over the Cascades. There was no satellite navigation, no ground proximity warning, no terrain database, no moving map. Position was a calculation, updated by radio bearings when they could be received. And in between updates, it was arithmetic performed on a knee board. 9,000 feet is also 5,400 feet below the summit of Mount Rainier. On that route, Rainier, terrain clearance was not a function of altitude. It was entirely a function of lateral accuracy. Fly the correct line, and 9,000 feet is a comfortable cruise over foothills. Drift east of it, and there is a wall. South of Portland, the wind changed. It came around out of the west at about 70 miles per hour. That is the whole accident, and it is worth taking slowly because it is the least dramatic killing mechanism in this entire story, and it is pure geometry. An aircraft flying north with a strong crosswind from the left does not get blown sideways in any way the crew can feel. There is no sensation of drift inside a cloud. The airplane flies straight ahead through the air mass, and the air mass itself is moving east at 70 miles per hour. A transport cruising around 150 to 170 miles an hour, uncorrected, gets pushed off its intended track by roughly 25 degrees. The Navy's determination afterward was exactly that. The plane was blown off course by high winds, pushed about 25 degrees east of its intended path. 25 degrees, held for 100 miles, puts you more than 40 miles east of where you think you are. In western Washington, 40 miles east of that airway, is Mount Rainier. 4 of the 6 aircraft turned back and landed at Portland. 1 continued and landed at Seattle. Those decisions were made in the same weather, on the same day by crews with the same information. which is the detail that resists any simple story about recklessness. This was not one crew ignoring a warning while everyone else went home. It was a marginal day on which reasonable people made different calls, and 5 of the 6 calls were survivable. Aircraft 39528 did not arrive. There was no distress transmission establishing what happened, and no confirmed radio contact that fixed its position at the end. It simply stopped existing on anyone's list of expected arrivals. The search that followed is the part that gets skipped in most retellings, and it is the part that demonstrates a permanent feature of this mountain. A search begins with a question nobody can answer. Where? The aircraft's last reliable position was old. The wind that displaced it was known only in general terms. The search area, defined honestly, was thousands of square miles of the Cascade Range in December, most of it forest, much of it above 5,000 feet, all of it under weather. Aircraft are the fast answer to a large search area, so the Navy launched them, and the weather grounded the search fleet for a solid week. That is not a delay in the administrative sense. The Cascades in December sit under a conveyor of Pacific systems, cloud bases on the deck. Icing conditions through the useful altitudes, mountain obscuration total. Sending search aircraft into it would have produced more wreckage. Ground parties went out into the country they could reach. Their problem was the reverse of the air crews. They could see, but they could see almost nothing because you can only search on foot what you can walk to. And by mid-December, the approaches into Mount Rainier National Park and the surrounding high country were snowed in. Even if searchers had guessed the correct glacier, the wreckage was already being buried. Snow accumulates on Rainier's upper glaciers in amounts that get measured in tens of feet a season. An aircraft that hits a glacier in early December is under winter by Christmas. After about 2 weeks, the search was suspended. Think about what that sentence does to 32 families. Not confirmed dead, not found. The record simply stops in a mountain range in winter, with no site, no remains, and no explanation beyond an estimate about the wind. For the families of the men on 39528, the next 7 months contained nothing at all. The mountain kept them. Then the mountain gave them back, and it did it through the exact process that produces the hazard in the river valleys below. On July 21, 1947, Bill Butler, an assistant chief ranger at Mount Rainier National Park, climbed to about 9,000 feet on Success Cleaver, a rib of rock on the mountain's south side, and glassed the South Tahoma Glacier with binoculars. Butler was not conducting a formal search. The search had been over for 7 months. He was a ranger who had spent years on that mountain and knew what its glaciers were supposed to look like. And summer had done what summer does: stripped the winter snow off the lower glacier surfaces and exposed whatever the winter had covered. Somewhere in that field of ice and rubble he found something that did not belong, a shape he became convinced was part of an aircraft protruding from melting snow. 2 days later, he led a party of 4 mountaineers onto the glacier. Glacier travel in 1947 involved rope, ice axes, hobnailed or early crampon-equipped boots, and judgment. The South Tahoma is not a technical climb, but it is a working glacier, which means it is riddled with crevasses, some of them covered by unstable snow bridges, and it is actively shedding rock and ice in summer. They found the front portion of the aircraft embedded in the wall of a deep crevasse. That is where the recovery problem became unsolvable. The wreck was not sitting on the surface. It was in the ice, in a crack, on a moving glacier, at altitude, in a place where the standard method of getting a body out involves lowering people on rope into a feature that periodically closes, opens, or drops chunks of its own wall. Recovery efforts in August 1947 reached the crushed nose section and found the remains of 11 servicemen inside. The military ended the operation there. The reason given was twofold, and both halves are documented: the extreme danger and instability of the glacier and the request of the families. Those families, having waited 7 months for any word, were told what conditions were, and asked that no more men be put into a crevasse on a moving glacier to retrieve people who were already dead. The recovery was abandoned. All 32 remain on the mountain. There is a memorial to them in the park, near the Lake George and Gobbler's Knob trailhead off the West Side Road past Ashford. Memorial Day services have been held for these men for decades, and they are still held 80 years on for a crash whose victims were never brought down. Look at what actually solved this case, not the search. The search failed completely, and it failed for reasons no amount of effort could have overcome. The area was too large. The weather grounded the aircraft for a week. The ground was inaccessible, and the snow was accumulating faster than anyone could look. What produced the answer was seasonal melt, 7 months later, exposing the wreck to a man who happened to be standing in the right place with binoculars in July. The mountain's ice hid 32 men in a matter of days and then, on its own schedule, offered part of them back. That is the same ice, on the same flank, doing the same thing it does with everything else it captures. And it is worth being precise about the mechanism, because it connects this crash directly to the hazard downstream. A glacier is not a frozen lake. It is a slow river of ice under its own weight, flowing downhill, cracking where it accelerates, carrying whatever falls onto it inside its body, grinding rock into flour at its base, and melting at its lower end. Anything that lands on the upper glacier gets buried by the next snowfall, incorporated, transported downslope over years and decades, and eventually delivered to the terminus. The wreck of 3D9528 is not parked. It is in transit and has been since 1946. And the same glacier that swallowed those Marines has a documented habit of expelling water without warning. The South Tahoma Glacier is the source of the roar the Volunteer heard in 2015. It sits at the head of Tahoma Creek, and it is the single most active producer of glacial outburst floods on Mount Rainier. Water accumulates in cavities within and beneath the ice, particularly in hot weather when melt is rapid or during heavy rain, until whatever is confining it fails. Then it leaves all at once, and it does not leave clean. The floodwater picks up the loose sediment stacked in the valley below the glacier, bulks up into a debris flow, and goes down Tahoma Creek, doing what debris flows do. 2 months after the recovery on the South Tahoma was abandoned, the mountain provided a full-scale demonstration on the adjacent drainage. On October 2nd, 1947, a debris flow came down Couts Creek in the southwest corner of the park, and it remains the largest such event since the park was established. It moved on the order of 40 million cubic meters of sediment. Where it crossed the main road into the park, the Nisqually Road that carries every visitor toward Longmire and Paradise, it buried the roadway under about 9 meters of mud and debris. 28 feet. The road did not wash out. It was interred, along with a stretch of forest, and the ghost forest of dead trees standing in that deposit is visible from the Couts Creek pullout today. No eruption, no earthquake, a wet autumn, a glacier releasing stored water, and a valley full of loose material waiting to be mobilized. There is a pattern here that keeps repeating with different actors. The Nisqually River destroyed or damaged bridges in 1926, 1932, 1934, and again in 1955. Debris flows have buried roads, wiped out picnic areas, and erased trails throughout the park's history. None of these events made national news. All of them were the same physical process that produced Osceola and Electron, running at small scale, on a schedule of years rather than centuries. As for aviation, the technology did improve, and it improved exactly the thing that killed 39528. Modern transports carry inertial and satellite navigation that fixes position continuously and independently of wind, which eliminates the 25-degree drift error entirely. They carry terrain awareness and warning systems that hold a database of the world's mountains and shout a warning when the aircraft's projected path intersects rock. Air traffic control radar and, later, automatic position reporting mean that a transport crossing western Washington is watched continuously by people on the ground who can see it deviating. Every one of those improvements addresses the navigation problem. None of them addresses the search problem. If an aircraft goes into the ice on Mount Rainier today, the position is known within a few hundred feet, which is an enormous advance, and the recovery is still limited by exactly what limited it in 1947: weather, altitude, crevasse hazard, active icefall, and the fact that a glacier is a moving object that does not agree to hold still while people work on it. Which brings up the thing the ice does that no instrument has ever predicted. It does not just carry. It falls. On the morning of June 21st, 1981, 29 people were on the Ingraham Glacier, high on the southeast side of Mount Rainier, on a guided summit climb run by Rainier Mountaineering, Inc. The clients had paid $150 each. Most of them were not mountaineers. They were people who had signed up for a guided ascent of the most famous peak in Washington, taken the basic snow school on the lower glacier, slept a few hours at Camp Muir, and started up in the dark like thousands of others before them. The route was the standard one, up through Cathedral Gap and across the Ingraham Glacier toward Disappointment Cleaver, the most heavily traveled line on the mountain. The one guiding companies had used for decades precisely because it is the least technical and the best understood. Above them stood the Ingraham Icefall. An icefall is what a glacier does when it flows over a steep step in the bedrock. The ice cannot bend fast enough, so it fractures into a chaos of towers and blocks called seracs, some of them the size of buildings, all of them leaning downhill, all of them moving. The Ingraham Icefall was known. It was on every map, it was visible from the route, and everyone crossing beneath it understood in general terms that ice falls out of ice falls. What nobody could do, then or now, was say when a particular block would go. Conditions that morning were not right. The guides scouting ahead judged the route above too dangerous, and the decision was made to turn the group around. The party had paused on Ingraham Flats, a relatively level bench of glacier that had served as a rest and staging area for generations of climbers, and they were in the process of getting the group back down. That is the sentence to hold on to. They had already made the correct call. The mission had already changed from summit to descent. The professionals had assessed the situation, reached a conservative conclusion, and were executing it. Just before 6 in the morning, a section of the Ingraham Icefall, roughly 300 feet wide, broke loose and fell about 800 feet. Guides positioned at Disappointment Cleaver watched it happen. The ice wall shattered, the mass struck the mountainside below, and it came apart into an avalanche of ice blocks and snow moving down onto the flats. People on the glacier heard it before they could see what it meant, and there was time to move, but not far. Climbers ran in their rope teams, in groups of 5, downhill and out to the side. Some of them made it out of the path. 11 did not, 10 clients, and 1 guide. The debris did not simply bury them under a snowslide that could be dug out. It swept them into a crevasse and filled it with tons of glacial ice. The rescue began immediately because the rest of the party and the guides were right there, and it ran into the first hard limit within minutes. Digging in avalanche debris made of ice blocks is not shoveling snow. The deposit sets up dense and irregular, blocks weighing hundreds or thousands of pounds interlock, and the crevasse below it may be tens of meters deep. A 19-member search party was organized and went to the site. Severe snowfall and gale-force winds moved in, which on the upper mountain means whiteout. Wind chill well below freezing, and the constant possibility of more ice releasing from the same icefall onto the people working beneath it. They found no one. The 11 were entombed in the crevasse under the ice that killed them, and recovery was determined to be impossible. They are still there, and the Ingraham has been carrying them slowly downslope ever since, in the same way it carries everything else that lands on it. A National Park Service Board of Inquiry examined the accident. Its conclusion was that this was a random event related to glacial movement, that it could not have been predicted, and that the guides were blameless. They had taken the party up the safest and most heavily traveled route on the mountain, they had made a conservative decision about conditions, and they had been in the process of retreat. That finding is more disturbing than a finding of negligence would have been. Negligence can be trained out. Procedures can be rewritten. What the board described was a hazard with no predictive signature and no procedural fix. A piece of a moving glacier detached at a moment of its own choosing and landed on the standard route, and the only mitigation available is to spend less time underneath it, which every guide on the mountain already knew. 11 dead in a single event made it the deadliest mountaineering accident in American history, and more than 40 years later, that is still true. The lesson the mountain kept teaching after 1981 was not about turning around at the right time. It was about the fact that on Mount Rainier, the ground itself is in motion, on the glaciers as surely as in the river valleys. And the motion is not correlated with human decisions in any usable way. 33 years later, the mountain made the same point with better equipment. In late May 2014, a party of 6 set out to climb Liberty Ridge, on the north side of Rainier. Liberty Ridge is a serious alpine route, not the tourist line. A steep rib of rock and ice rising between the Willis Wall and the Liberty Wall, with objective hazard from rockfall and icefall on both flanks, committing enough that retreat from high on the route is harder than continuing. The party consisted of 4 clients and 2 guides from Alpine Ascents International, Matthew Hegeman, 38, and Aiton Green, 28, both experienced professionals on a route they knew. They had a satellite phone. They had avalanche transceivers, the small radio beacons climbers wear so that a buried person can be located by their partners. They had modern weather forecasting available before departure and modern gear on their bodies. They checked in. The last contact was a satellite phone call from one of the guides at about 6:20 in the evening on Wednesday, May 28th, from a camp high on the route at roughly 12,800 feet. Nothing in that call reported an emergency. When the party did not come off the mountain, they were reported missing on May 30th, and the search began with an advantage the 1946 crews never had. Rangers knew, within a few hundred meters, where these people had last been. Helicopters flew the north side. Searchers picked up signals from avalanche beacons on the glacier at the base of the wall, 3,300 feet below the last known campsite, along with climbing equipment scattered on the ice. 3,300 feet is not a fall anyone survives. What happened has never been established with certainty. There was no distress call, no witness, and no recoverable evidence beyond the debris field. The available evidence suggests the party was swept from the route, most likely by an avalanche or rockfall coming from above during the night, and that they fell together. The exact sequence remains unknown. Then came the second half of the problem, and it was 1947 all over again. The debris lay in a zone under active rockfall and icefall from the Willis Wall, one of the most dangerous pieces of terrain in the contiguous United States, on a glacier surface riven with crevasses. Park officials assessed a ground recovery and concluded that putting rescuers into that location risked killing them for no possible benefit to people who were already dead. The recovery was called off. 6 bodies remain on the mountain. Compare the 2 searches honestly. In 1946, it took 7 months and a chance sighting through binoculars to find the wreck. In 2014, it took a matter of hours to find the debris field because the party carried transmitters and a satellite phone and had reported their position. The technology closed the location gap almost entirely. It did not move the bodies 1 inch. The recovery limit is set by the terrain and by what the mountain is doing to the terrain, and no advance in electronics has touched it. That is the pattern this mountain keeps generating in different forms. Better tools tell you what happened, faster and with more precision, and the physical situation stays exactly as intractable as it was in 1946, which is a manageable frustration when the subject is 6 climbers on the north face. Move the same principle down to the valleys, where the ground itself is the thing in motion, and 90,000 people are standing on it, and it stops being manageable. Start with what arrival actually means. because the word lahar has been doing a lot of work in this story without ever being cashed out into what happens to a street. The modeled flow depth for a large lahar coming into the Orting area is on the order of 10 meters, 30 feet of moving material, top to bottom, filling the valley from wall to wall, with a density roughly twice that of water because most of it is rock and sediment rather than liquid. Buildings do not resist that. A wood frame house is engineered to carry its own weight downward and to resist wind loads sideways, and wind is a fluid with a density of about 1¼ kilograms per cubic meter. This mixture arrives at close to 2,000. The lateral force on a wall is not comparable to a storm by any factor that matters, and before the force question is even settled, there is a buoyancy question, because a sealed wooden structure in a dense fluid tends to lift off its foundation. Houses in the path of large lahars are typically shifted, broken up, and incorporated into the flow, and what stays behind is the flat gray surface. The flow also carries ammunition, boulders in suspension, whole trees stripped of branches, sections of bridge deck, vehicles, and the remains of whatever it destroyed a mile upstream, all of it moving at the speed of the flow front. Bridges fail from a combination of impact, of scour at the piers, and of simply being lower than the flow is deep. Then it stops, and the second phase begins. And this is the phase that emergency planners find hardest to explain to the public. The deposit is not a lake of mud that drains away. Water leaves the mixture, the sediment consolidates, and it firms up into something with the consistency of setting concrete. Heavy machinery cannot immediately drive on it, and neither can people walk on it reliably, and anything caught in it is held by a material that resists digging. At Armero in 1985, the most agonizing part of the response was not the search. It was that rescuers reached people who were alive and trapped in the deposit and could not extract them for days with the equipment available. Now think about who does the extracting in a valley where the roads are under the deposit, the bridges are gone, the water mains and power lines are severed, and the hospital that would receive casualties is in the same valley that just got filled. Rescue in this scenario is not delayed by weather or distance in the way it was for the Marines on the South Tahoma Glacier. It is delayed because the flow eats the infrastructure that rescue runs on, in the first 10 minutes, along its entire length. That is a permanent feature of this hazard, and it is why the entire public strategy is evacuation rather than response. Once the flow has passed, the people who did not get to high ground are beyond the reach of any organization that exists. Then look at what would be under it. The Puyallup Valley carries State Route 162 and 410 rail lines that have run since the 1880s, farms, schools, and a chain of towns that are now suburbs. The White River Valley delivers into Auburn and Kent, which is one of the densest warehouse and distribution corridors on the West Coast, sitting on Osceola ground, threaded by mainline rail and by State Route 167. Downstream of all of it is the Port of Tacoma, built on the delta, the Osceola mud flow created when it filled the arms of Puget Sound 5,600 years ago. And the damage does not end when the flow does. Mount St. Helens established that beyond argument, about 50 miles from Rainier as the crow flies. The 1980 eruption dumped an enormous mass of debris into the upper North Fork Toutle River, and the rivers spent the following months exporting it downstream. Sediment moved down the Toutle into the Cowlitz and out into the Columbia, and it filled the Columbia's shipping channel, which had been maintained at 32 feet down to about 12 feet, stranding a ship in the middle of it. The Army Corps of Engineers ran emergency dredging for 8 months to reopen the navigation channel, removing on the order of 100 million cubic yards of material from the three rivers. That is what a river system does with a sudden sediment load. It carries it to the sea, slowly, through every town on the way, and it raises its own bed as it goes, which means the flood risk in the valley increases for decades afterward for ordinary rainfall that used to be harmless. The Corps eventually built a sediment retention structure on the North Fork Toutle, completed at the end of 1989, specifically to hold the material back. It was nearly full by 2012, and sediment has been overtopping it and heading downstream since 45 years after the eruption that produced it. Apply that arithmetic to Rainier. The electron mud flow buried 13 square miles of the Puyallup Valley in a single afternoon in 1507, more than 26 feet deep at its thickest. A comparable event today would leave the valley's rivers to redistribute that sediment through the Puyallup, into Commencement Bay, and into a working port for years, while every community along the corridor discovered that its flood maps had been rewritten by a process that was over in an hour. That is what unmanageable means in concrete terms. Not a dramatic day. A permanent change to the landscape that the survivors then live in. And this is exactly why the small events matter so much. Nobody gets to study the big one in advance. What the mountain provides in an accessible valley every few summers is a working miniature. The same physics, the same transformation from water to debris flow, the same acoustic signature, the same infrastructure damage, at a scale that closes a gravel road instead of a county. Go back to Tahoma Creek, because that valley has been running the experiment continuously since 1967 in public, at a scale small enough to survive and large enough to teach. Since 1967, that one drainage has produced a long series of debris flows, nearly all of them starting as outburst floods from the South Tahoma Glacier. At least 23 were documented by the early 1990s. Between 1986 and 1992 alone, the glacier released 15 outburst floods, at least one in every one of those years. The 2015 event the volunteer heard and the 2019 event that closed the road again are later entries on the same list. This is not a rare phenomenon that geologists study through deposits. It is a recurring summer event in a national park with a road running through it. The trigger is weather, and the weather that does it is not what people expect. These floods come during periods of unusually hot or unusually rainy weather in summer or early autumn. Heat drives rapid melt at the glacier surface. That water works its way down through the ice to the bed, where it collects in cavities and passages. When the input rate outpaces what the drainage system can carry, pressure builds until the confinement fails, and then a volume of water that took days to accumulate leaves in minutes. The water alone would be a nuisance. What makes it dangerous is what is waiting below the glacier. The lower Tahoma Creek Valley is packed with loose sediment, rock flour, gravel, boulders, and the debris left behind by a glacier that has been retreating and thinning. During the retreat earlier in the 20th century, masses of ice were stranded in the valley, cut off from the flowing glacier. And that stagnant ice has been melting out ever since, releasing the sediment frozen inside it. The valley floor is a loaded hopper. Send a wall of water through it, and the water bulks up into a debris flow within a short distance, and the flow arrives downstream carrying 10 or 20 times the mass that left the glacier. The aggradation has been measured. In parts of Tahoma Creek, deposits accumulated at close to 0.5 meter per year after 1988. The valley floor is rising, which means the channel that engineers designed a road bridge for in one decade is a different, higher, wider channel the next decade, and the flow does not have to be bigger to do more damage. It only has to arrive in a valley whose floor has come up to meet the infrastructure. That is why the West Side Road, which once carried visitors along the mountain's southwest flank toward Clapatchie Point, has spent decades being damaged, repaired, closed, and reassessed. The park did not lose that road to a single catastrophe. It lost it to a process that keeps returning every few summers on a schedule set by heat waves. Then, in the autumn of 2006, the mountain demonstrated the other input. On November 6 and 7, Mount Rainier National Park received 18 inches of rain in 36 hours. Not on the summit as snow, as rain, across a huge swath of the mountain, falling onto an existing snowpack and running off almost immediately because saturated volcanic soil on a steep slope has no capacity to absorb that volume. Every river coming off the mountain went to flood at once, and these are not gentle rivers even on a calm day. The Nisqually, the Couts, the White, the Carbon, the Puyallup, all of them steep, all of them carrying beds of loose glacial sediment. The flood was assessed as a 100-year event, and it did what a 100-year event does in a park whose entire infrastructure occupies valley bottoms, because that is where the flat ground is. Sunshine Point Campground, just inside the Nisqually entrance, was destroyed. The river took the ground it was built on and did not give it back. The campground was never rebuilt. Couts Creek flooded across the road again, 60 years after burying it in mud. The Nisqually to Paradise Road, the main artery of the park, was damaged in multiple places. Longmire took damage. Trails, bridges, culverts, and utility lines were destroyed across the park. Mount Rainier National Park closed for 6 months. The gates reopened on May 5, 2007. For a park that receives well over 1 million visitors a year and anchors the economy of the small towns along its approaches, that is an extraordinary consequence for 2 days of rain. No eruption, no landslide off the summit, water, arriving faster than the landscape could pass it, in a place where the landscape is steep, young, and full of loose material. Now put the two triggers side by side, because between them, they define the modern hazard in the park itself, heat and rain. Neither one is a volcanic process. Both of them are getting more attention as the climate changes, and this is exactly the place where it is easy to overstate a conclusion. So here is the careful version. Mount Rainier's glaciers have thinned and retreated substantially over the last century, and the retreat has continued. Researchers have explicitly asked whether the recent frequency of debris flows on the mountain is a climate warming signal, and the question is legitimate. Warmer summers produce more intense melt events, more rain on snow at higher elevations, more exposed unconsolidated sediment where ice used to be, and more slopes that lose the ice that was holding them together. What cannot be said honestly is that retreating glaciers simply make Rainier more dangerous, or simply make it safer. Both statements are available and both are too clean. Less ice on the mountain means less material available to melt into a lahar during an eruption, which is a genuine reduction in one hazard. Less ice also means more freshly exposed, unstable, unvegetated debris in the upper valleys, more stagnant ice melting out and releasing sediment, and steeper, unsupported slopes where the ice used to press against the rock. The propensity of a given glacier to produce outburst floods is not a simple function of how thick it is. South Tahoma has produced dozens of these events across a period when it was doing nothing but shrinking. The defensible statement is narrower and more useful. The current, unusually active phase of debris flows at Mount Rainier coincides with a period of substantial ice retreat and thinning. The physical connections between those two facts are plausible and partially documented, and the process is producing hazardous flows in the park every few years without any volcanic involvement whatsoever. This is where the small events pay for themselves, because they gave engineers something almost no volcano hazard program ever gets: a common, repeatable version of the catastrophic event, happening in an accessible valley often enough to test equipment against. If you want to build a machine that can recognize a lahar and sound an alarm before it arrives, you need to know what a lahar sounds like to a sensor, how it differs from an earthquake, a rock fall, a thunderstorm, a helicopter, or a truck on a gravel road. You cannot wait for the next electron mudflow to collect that data. You can, though, put instruments in Tahoma Creek and wait for July. Instruments are cheap compared with the other thing these valleys keep accumulating, which is people. Mount Rainier National Park drew about 1.1 million visits a year in 2008, and more than 1.7 million by 2021. The use is not spread evenly across the calendar or the map. Roughly 70% of it lands between July and September, and it concentrates into a small number of destinations. Paradise on the south side, Sunrise on the northeast, the trailheads, the campgrounds, the roadside viewpoints, where a family can park and eat lunch with the mountain filling the windshield. Look at where those places are. Paradise sits at 5,400 feet in the upper Nisqually drainage, reached by a single road that climbs the valley from the Nisqually entrance through Longmire. Sunrise sits above the White River Valley, reached by a road that climbs from the White River entrance, past a campground that a rock avalanche stopped half a mile short of in 1963. The visitor infrastructure is in the drainages, because the drainages are how you get up a volcano without building a road on a knife-edge ridge, which means the summer population of the hazard corridors is not just the residents of Orting and Sumner and Buckley. On an August Saturday, it includes several thousand visitors distributed along valley roads inside the park, most of them from out of state, many of them from countries where nobody has ever heard a lahar siren, all of them with no idea what the acoustic warning of a debris flow sounds like, and none of them positioned to walk 2 miles uphill through old-growth forest on unfamiliar ground. The park knows this. It is one reason the detection network kept expanding into the Tahoma Creek and Nisqually drainages. The corridor that carries the main entrance road, Longmire, and the traffic to Paradise. It is also why the seasonal message from park staff about debris flows is unusually blunt for a national park. If you are near a river channel and hear a roaring sound, or feel the ground shaking, or see the water suddenly turn muddy and rise, move away from the channel and get to high ground immediately. Do not stop to film it. Do not wait to see what it is. That advice is not decoration. It is the same protocol that saved 2 volunteers at Tahoma Creek in 2015. And it is the only protocol available inside the park, because a siren network that covers the towns cannot cover 100 miles of backcountry trail. Add the climbers. Thousands of people a year attempt the summit, most of them on 2 routes, and they spend their nights at Camp Muir at 10,000 feet, or Camp Sherman at 9,500, sleeping directly on the glaciers, upslope of everything. A collapse of the west or northeast flank would begin above them or beside them, and the ones on the mountain would be the first people to know briefly. The Nisqually Valley below the park carries its own communities. Ashford, Elbe, National, and the small settlements strung along State Route 706. 706 exist to serve the park and the timber industry, and they sit in a valley that the National Lahar ran down for at least 100 kilometers 2,200 years ago. Pierce County's emergency management now operates dozens of sirens across the Puyallup and Nisqually River valleys, 42 of them at last count, which is a number that tells you how much ground has to be covered on the audio side alone. Everyone in those valleys, resident or visitor, is relying on the same thing: that a machine will notice a flow, that a human will believe the machine, and that an alarm will reach them in time to matter. The best evidence for what happens when that chain breaks does not come from Washington. It comes from Columbia, and it is the reason the American system exists in the form it does. It is also the single most instructive human failure in the history of this hazard, and every emergency manager in Pierce County knows the name of the town. On November 13, 1985, Novato del Ruiz in Colombia produced an eruption that volcanologists do not even classify as large. Heat from it melted part of the ice cap on the summit, not most of it. Estimates afterward indicated something like 90% of the ice was still sitting up there when it was over. That fraction was enough to generate 3 lahars, which went down the drainages, and one of them ran roughly 40 kilometers to the town of Armero, on flat ground that earlier flows from the same volcano had delivered centuries before. More than 23,000 people were killed. The reason that number matters here is not the size of the eruption. It is everything that existed beforehand and failed to matter. Scientists had been watching the volcano. A month before, researchers, including Marta Lucia Calvache Velasco, of what is now the Colombian Geological Service, had submitted a report to the Colombian Congress laying out the volcano's history and warning that an eruption was likely within months or years. In October, geologists published a hazard map that showed Armero could be completely flooded in the event of a major eruption. That map was criticized as too alarming. Read that phrase again because it is the most dangerous sentence in volcano hazard management, and it is available in every language. A hazard map is a statement about what the ground has already done. Calling it alarmist is a statement about how the audience feels. The two are not in conversation with each other, and only one of them is negotiable. The flows took more than 2 hours to travel from the volcano to Armero. 2 hours is an enormous amount of time. It is more than double the window Pierce County has modeled for Orting. In those 2 hours, the information that mattered existed in the world, held by people who understood it. What did not exist was a mechanism that converted that knowledge into 23,000 people walking uphill. And the available accounts describe residents in the valley being reassured rather than evacuated, unaware that the geography they lived on made the town exceptionally exposed. Armero was not destroyed by a lack of science. It was destroyed by the distance between science and a person deciding to walk uphill. 4 years later, when Nevado del Ruiz erupted again, there was no loss of life, because by then the warnings, the maps, and the protocols were connected to an actual response. The American reaction to 1985 was institutional, and it was fast. The USGS built the Volcano Disaster Assistance Program to put teams and instruments on dangerous volcanoes anywhere in the world on short notice. An outfit created specifically so that no observatory anywhere would again watch a lahar hazard develop without the hardware to detect it. The acoustic flow monitor, the buried sensor that listens for the specific tremor of a moving debris flow, came out of that same program of work. It was field-tested on volcanoes where debris flows were frequent, and it was installed on Mount Rainier in 1998 to protect the towns in the Puyallup and Carbon valleys. That is the direct line. 23,000 people died on a floodplain in Colombia, and 13 years later, a county in Washington state began burying microphones in riverbanks below a mountain that has done the same thing repeatedly on a larger scale. There is one difference between the two situations that should not be comforting. Armero's warning came from an eruption that was visible, audible, and had been building for months. Everyone knew the volcano was restless. The failure was in the last mile, in communication and decision-making. At Mount Rainier, the failure mode that the geology most clearly documents does not include an eruption at all, which removes the entire early warning phase that Colombia had and wasted. There is no month of restlessness, no ash on the snow, no public argument about whether the hazard map is too alarming. There is a slope that has been weakening for centuries, and then there is a flow in the valley. And the only interval available for a decision is the one between a sensor recognizing a signal and a wall of mud arriving at the schools, which is why the Rainier system has to work with a margin nobody in Colombia would have recognized as a margin at all. And it is why an event that happened on the east side of the mountain on a winter day in 1963 is worth studying carefully, because it shows exactly how thin the geography's tolerance is and how much of the outcome came down to the date on the calendar. Little Tahoma Peak is the jagged remnant that stands off Rainier's east flank at 11,138 feet, a leftover fin of the older volcano that the modern cone grew around. Its north side rises above the Emmons Glacier, the largest glacier by area in the contiguous United States, which flows down into the White River Valley. On December 14, 1963, very large masses of rock fell off the north side of Little Tahoma onto the Emmons. Not one fall, at least 7 separate avalanches with a total estimated volume of about 14 million cubic yards. For scale, that is enough rock to bury a square mile under about 13 feet of rubble, and it came off a single peak over a short period in midwinter. The debris hit the glacier and ran. It descended as much as 6,200 feet in elevation and traveled about 7 kilometers down the Emmons Glacier and out into the White River Valley. Calculations based on how high the deposits ran up onto the valley walls, the same banking evidence used for the ancient lahars, indicate the avalanches were moving at least 80 to 90 miles an hour, with some estimates higher. Rock does not normally do that. A dry rock avalanche is a high-friction event. It should have piled up on the upper glacier and stopped. The USGS study of the deposits attributes the unusually long runout to a cushion of trapped and compressed air at the base of the moving mass, which buoyed the debris and cut the friction against the ground. The avalanche essentially hovered on the air it was overrunning. That mechanism is why some rock avalanches around the world travel distances that simple friction calculations say are impossible. And it is why an event on the upper mountain can arrive somewhere people consider safely distant. The debris came to rest less than half a mile from the White River campground. In December, that campground was closed and empty. In August, the White River campground holds families in tents, cars parked in loops, kids in the river, and a trailhead parking lot full of climbers starting up the standard route to Camp Sherman. The rock avalanche that stopped short of it was moving at highway speed and would have arrived with essentially no notice. A sound. Then debris. In a valley where the walls are far enough apart that running out of the path is not obviously possible. What set it off is the detail that ties this event back to the mountain's chemistry. The initial rockfall may have been caused by a small steam explosion near the base of Little Tahoma Peak. A steam explosion is what happens when hydrothermally heated water in a confined space flashes to vapor and expands violently, and it is precisely the kind of event that the entire volcanic monitoring toolkit is worst at anticipating. It requires no new magma. It produces no meaningful precursors that anyone has learned to read. It comes out of the same hot, wet, chemically active plumbing that has been converting the mountain's rock to clay for thousands of years. There is an epilogue to that avalanche that says something about how physically odd this mountain is. The rock debris spread across the lower Emmons Glacier in a thick blanket, and rock is a good insulator. Shielded from summer sun by its own rubble, the ice underneath melted more slowly than it would have, and glaciologists connect that debris cover to a subsequent advance of the Emmons Glacier in the following decades, at a time when most glaciers in the range were retreating. A collapse from the mountain caused one of its glaciers to grow. Now assemble what the 20th century actually recorded on Mount Rainier, without a single eruption in any of it. An aircraft flew into the south side in 1946 and vanished for 7 months. A rock avalanche moving at 80-plus miles an hour crossed 7 kilometers of glacier and valley in 1963 and stopped short of a campground by half a mile. A debris flow buried the main park road under 28 feet of mud in 1947. Outburst floods came out of the South Tahoma Glacier in at least 15 separate events in 7 years during the late 1980s and early 1990s. An icefall dropped a 300-foot wide slab of glacier onto the standard climbing route in 1981 and killed 11 people during a retreat. A storm in 2006 closed the entire national park for 6 months. 6 climbers disappeared off Liberty Ridge in 2014 and are still there. Not one of those required magma to reach the surface. All of them are the mountain operating normally. That is the reframing this story has been building toward, and it is worth stating plainly, because it inverts the way most people think about volcanoes. At Mount Rainier, an eruption is not the hazard. An eruption is one of several possible triggers for the hazard, and not the most likely one. The hazard is 14,000 feet of ice-loaded, chemically weakened rock standing over 5 river valleys full of people, in a climate that delivers both heat waves and atmospheric rivers, on a slope that is already creeping. Which leaves the emergency managers of Pierce County with a problem that has no good solution and one workable, partial answer. You cannot predict the failure. You cannot stop the flow. You cannot move the cities. What you can do is try to win the only race that remains, the race between a wall of mud descending a valley at tens of miles an hour and a population that needs to walk uphill. To have any chance in that race, you have to know the flow exists within seconds of it starting, and you have to be believed. The Mount Rainier Lahar detection system has been running since 1998, and its founding idea came out of the small events in the park. The original instruments were acoustic flow monitors, built by the USGS and installed in the drainages that a lahar would use. An acoustic flow monitor is a sensor buried in the ground beside a river channel that listens for vibration in a specific frequency band, the band that dense sediment-laden flows generate as they scour and grind their way down a valley. The important part is not that it hears something, everything makes the ground shake. The important part is what the signal looks like over time. An earthquake produces a sharp burst that decays within seconds. A truck produces a brief signature that comes and goes. A lahar produces something different, a sustained building tremor that lasts for minutes and grows as the flow front approaches, then stays high as the body of the flow passes. That shape, that duration, that band is a recognizable fingerprint. And the only way to learn it well enough to trust it is to record real flows. Tahoma Creek, with its outburst floods every year or two, was the classroom. The system built on that foundation is now considerably more than a set of buried microphones. The Rainier Lahar Detection Network, operated and upgraded by the USGS Cascades Volcano Observatory, together with the Pacific Northwest Seismic Network, includes tens of instruments across the volcano's flanks and down the vulnerable valleys. Since 2016, it has been rebuilt with newer equipment, about 20 sites carrying broadband seismometers that transmit continuous real-time data, plus infrasound sensors, tripwires, web cameras, and GPS receivers that measure ground deformation to the millimeter. Infrasound is the piece worth understanding, because it works on a principle most people have never considered. A large mass moving down a valley pushes air, and it generates sound at frequencies below the range of human hearing, in the same way a distant explosion produces a pressure wave you feel rather than hear. Those low frequencies travel very well through the atmosphere, over ridges and around corners, and they carry the signature of the source. A USGS research seismologist at the Cascades Volcano Observatory, Weston Thelen, described the instrument without any romance at all. It is literally just a fancy microphone tuned to record things below our normal range of hearing. Put 3 of those microphones in a line across a slope, and something useful falls out. The pressure wave from a debris flow reaches each sensor at a slightly different instant, and the differences in arrival time let you triangulate the direction of the source. Not just that something is happening, but where the leading edge is, and which valley it is coming down. That distinction is not academic. A warning that evacuates the wrong valley costs credibility, and credibility is the fuel the entire system runs on. The array reduces false alarms, and a system that cries wolf is a system nobody walks uphill for. The network kept expanding because the coverage had holes. Approval came in 2022 to extend detection into the Tahoma Creek and Nisqually drainages on the southwest and south sides, the corridor that holds Ashford, Elbe, National, and the park's own main entrance road. More recently, 5 new monitoring stations went in on the east and northeast sides, including one near Crystal Mountain at around 7,000 feet, the first infrasound array on that side of the volcano. It covers the 2 forks of the White River, which means the communities of Greenwater, Buckley, and the outlying parts of Enumclaw are, for the first time, watched by instruments designed for their specific valley. Installing them is its own small logistics problem, and it explains why this took decades rather than a single budget cycle. There are no roads. A 600-pound equipment hut has to be flown in under a helicopter and set down on a ridge, then leveled, anchored against winter wind, and wired to solar panels, that run the station through the summer and to batteries that carry it through months of snow and darkness. Every station has to telemeter its data continuously to the observatory, which means a radio path over terrain, which means repeaters, which means more sites. The mountain generates the same problem for the people who monitor it that it generates for everyone else. The ground is steep, the weather is hostile, and the useful locations are the hardest ones to reach. At the far end of all that wiring are two emergency operations centers that operate around the clock. The data does not go to an automated siren trigger and nowhere else. It goes to people at Pierce County Emergency Management and at the state level, whose job is to look at what the instruments are reporting and decide whether it is a lahar. The alerting side is separate hardware. Pierce County maintains a network of all-hazard alert broadcast sirens in the cities and towns from Orting down through the Puyallup Valley to the port of Tacoma. They are pole-mounted, they are loud, and they carry a voice channel as well as a tone. The county tests them on the first Monday of every month for a couple of minutes at noon, which is why the whole valley knows the sound. The sirens are backed by phone, text, and email alerts through the county's notification system, and by wireless emergency alerts that push to every mobile phone in a geographic area, whether or not the owner ever signed up for anything. So the chain, end to end, looks like this. A flow starts somewhere on the volcano. Ground sensors and infrasound arrays register a sustained signal with the right character in the right band, and the location work identifies which drainage. The data reaches operations centers staffed 24 hours a day. Humans confirm. The sirens sound, the phones scream, and roughly 90,000 people in the mapped hazard zones are told that the thing they have practiced for is now happening. Every piece of that is a genuine achievement, built by people who have spent careers on it and who take the responsibility seriously. And it changes exactly one variable. Detection tells you the flow exists. It does not tell you the flow is coming before it starts. It does not slow it down. And it does not shorten the distance anyone has to travel to reach high ground. The instruments improved enormously between 1998 and today. The travel time from the mountain to the towns is set by gravity, valley gradient, and the density of the mixture, and it has not changed at all since 1507, which turns the entire problem into an arithmetic exercise with a brutal answer. Start with the clock. USGS scientists working with university researchers have modeled lahar behavior at Mount Rainier using a numerical model called D-Claw, which simulates how a mass of debris and water actually moves across real topography rather than assuming it behaves like water. Run a large lahar in that model, and it reaches the community of Orting in as little as 50 minutes. Across the hazard zones as a whole, the range that Pierce County plans against runs from roughly 40 minutes to as much as 3 hours, depending on where you are and which valley the flow chooses. Closer to the mountain, less time. Further down the Puyallup, more. On the steep upper slopes, these flows can move at speeds measured in the hundreds of miles per hour, and by the time they are in the lowland valleys, they are down to tens of miles per hour, which is still faster than anyone runs and faster than traffic moves on a 2-lane road with 3,000 cars trying to use it. 50 minutes is the whole budget, and it does not all belong to the people in the valley. Some of it goes to detection. The sensors need enough signal to be confident, and confidence takes seconds to a couple of minutes of sustained data. Some of it goes to confirmation, because a system that fires on every rockfall destroys itself. Some goes to activation, and to the physical time it takes sirens to sound and phones to alert. Some goes to the most human variable in the chain, which is the interval between a person hearing an alarm and that person actually moving. And the research on human behavior in disasters is consistent and unflattering. People seek confirmation first, they look out the window, they call someone, they check their phone. They ask a neighbor if this is real. Whatever is left is walking time. So consider what the region actually does about that, because it is one of the more remarkable pieces of civil preparedness in the United States, and it gets almost no attention outside Washington. On March 21st, 2024, more than 45,000 students in the Puyallup, Sumner-Bonnie Lake, Orting, White River, and Carbonado school districts took part in a coordinated Lahar evacuation drill, the largest such drill in the world. Roughly 13,000 of them walked, on foot, up to 2 miles each way, out of the mapped hazard zone to designated safe ground. The other 32,000 sheltered in place, at schools that already sit outside the zones. 3 emergency operations centers were activated to manage the movement. The drill runs on a 2-year cycle, and 2024 was the first time multiple districts evacuated simultaneously, 2 miles on foot. Work the arithmetic that a school principal has to work. A fit adult walking briskly covers 2 miles in about 35 minutes. A line of 6-year-olds does not. A line of 6-year-olds moves at the speed of its slowest child on a route that crosses roads, in whatever weather the morning provides, and it has to arrive with the group intact. Because a head count that comes up short at the safe zone means somebody has to go back down into the valley. Then add the people who cannot walk 2 miles at all. The hazard zones contain long-term residential care facilities, holding hundreds of residents, many of them non-ambulatory. They contain hospitals, clinics, and the ordinary distribution of people recovering from surgery, using oxygen, or simply 88 years old. They contain warehouses and industrial sites where thousands of people work day shifts, and a port. Evacuating a nursing home vertically or horizontally in 40 minutes is not a plan that survives contact with reality, and everyone involved knows it. Then, remove the daylight. The 2024 drill happened on a school day, in the morning, with staff on duty and children already assembled in buildings by class. A Lahar at 2 in the morning finds the same population asleep, distributed across bedrooms, with the children in the care of parents who will not leave without them and who will lose minutes gathering them, and with the roads carrying only the people who chose to drive. That is why the plan in Orting is to walk, and why the town is spending roughly $9 million on a bridge for pedestrians. The Foothills Trail runs through town along the old rail grade. The new structure lifts people from the trail over State Route 162 and up toward the higher ground on Rocky Road Northeast, with a second span planned to carry the route over the Carbon River and up the hill toward the plateau at Tehala. It is 20 to 30 feet wide, sized to pass about 12,000 people in 30 minutes. Consider what the width means. 30 feet of deck is not architecture, it is throughput. Somebody calculated how many bodies per minute can cross a given width at a fast walk, multiplied it against the population of the valley floor, and sized the structure to clear the town inside the modeled window. The design brief for that bridge was a stopwatch. The road bridges cannot do that job. There are only a handful of crossings out of the valley floor. They are low. They sit inside the zone the flow would occupy, and a Lahar in the Puyallup and Carbon channels would be a flood of mud, rock, and boulders that could stand something like 10 meters high as it comes through. Vehicles queue. A queue on a bridge in an inundation zone is the worst possible arrangement of people and geography, and it is what happens automatically if nobody has practiced anything else. Pierce County also regulates the ground itself. County code designates volcanic hazard areas and imposes requirements on what can be built in them, which is the quiet, unglamorous half of hazard management and the half that generates the most local friction because it collides directly with the value of flat, well-served land inside a growing metropolitan area. The valleys have kept growing regardless. Population in the Puyallup and White River corridors has risen for decades, and every new subdivision on the valley floor adds people to the count that has to move in 40 minutes. The count is now more than 90,000 people living within the mapped Lahar hazard zones around Mount Rainier. That figure is the reason the volcano ranks where it does in the National Threat Assessment, not the frequency of eruptions. The number of human beings standing on the deposits and the geologic record behind that number is not ambiguous. Within the past 6,000 years, at least 11 large lahars have reached the Puget lowland. 11. That is not a hypothetical hazard extrapolated from theory. It is a documented recurrence, layer by layer, in the ground under the schools that run the drills. That leaves the honest accounting for the entire modern effort, and it needs to be stated without softening. Between 1998 and today, the detection network went from a handful of buried sensors to a real-time array of broadband seismometers, infrasound arrays, tripwires, cameras, and GPS, feeding 2 staffed operations centers, backed by sirens, cell broadcasts, marked routes, region-wide drills involving tens of thousands of school children, and purpose-built pedestrian infrastructure. The lahar still takes the same 50 minutes. Every improvement has been made on the detection side of the equation, because that is the side that can be improved. Nobody has found a way to make the Puyallup Valley longer, or the flow slower, or the population smaller. The system's entire achievement is converting an event that would have arrived with no notice into an event that arrives with most of its travel time available for running. And the honesty of that trade is the strongest thing about the program. It is not a solution. It is a head start. There is one scenario in which even the head start compresses toward nothing, and it is the scenario the mountain demonstrated in 1507. A collapse from the west flank generates its lahar within about 2 kilometers of where it starts, high on the mountain, with the sensors on the flanks catching it almost immediately. That is the good case. The bad case is a failure that begins low, in a valley already occupied by people, in which case the first detection and the first arrival are close to simultaneous, and the sirens are a description of the present rather than a warning about the future. Nobody can rule that out, because nobody can see inside the mountain well enough to know which parts of it are closest to failing. What the instruments can do is tell us whether the machinery that manufactures those weak zones is still running. In July 2025, it answered that question loudly. At 1:29 in the morning, Pacific Time on July 8, 2025, the seismometers on Mount Rainier began recording earthquakes, and then they did not stop. By that morning, the rate had climbed to 41 located events per hour. Not 41 over the course of a day, 41 in 60 minutes every hour, a machine gun sequence of small ruptures under the summit. Over the following weeks, the network located more than 1,350 individual earthquakes, and thousands more were recorded but were too small to be located at all. It was the largest earthquake swarm ever recorded at Mount Rainier. Before you supply the obvious interpretation, look at the numbers that describe the individual events. The largest earthquake in the entire sequence was a magnitude 2.42 on July 11th. None of them were felt at the surface. Nothing was damaged. Nothing shifted visibly. No hiker at Camp Muir noticed anything. The quakes were concentrated at depths of roughly 1.5 to 4 miles beneath the summit, which in volcano terms is shallow, well above where a magma reservoir would sit. Through all of it, the USGS alert level and aviation color code for Mount Rainier stayed at green and normal. That combination, the largest swarm ever recorded paired with an alert level that never moved, deserves attention, because it is what a functioning monitoring system looks like when it refuses to be stampeded. There was precedent to compare against. In September 2009, a vigorous swarm of over 1,000 small, shallow earthquakes occurred beneath Rainier over 3 days, the largest daily count recorded since seismic stations were first installed on the volcano itself in 1989. Its largest event was a magnitude 2.3. Shorter swarms had come in 2002, 2004, and 2007, with fewer events but somewhat larger ones. The mountain has a documented habit of doing this, and it had never been followed by an eruption in the instrumental era. More useful than the pattern is the research into what causes it. Analysis of the 2009 swarm concluded that it was initiated by a sudden release of high-pressure fluid into pre-existing fractures, with the continuing activity driven by that pressure diffusing outward through the fracture network combined with stress transfer from each earthquake to the next. Past swarms at Rainier have been attributed to the circulation of fluids interacting with existing faults, which is to say the earthquakes were not rock-breaking because magma was pushing it aside. They were rock-slipping because pressurized water got into cracks that were already there and reduced the friction holding them shut. A fault that is stable when dry can slip when water at high pressure pushes its two faces apart, which is why fluid pressure is one of the most powerful triggers in all of seismology. To test whether the same thing was happening in 2025, the observatory needed to answer one question above all others. Is there magma involved? There is a direct way to check. Magma rising toward the surface carries dissolved gas, and as pressure drops, that gas comes out of solution and escapes, with sulfur dioxide as the most diagnostic component. Deep, old, cooling magma that is going nowhere does not deliver sulfur dioxide to the summit. Fresh magma on the move does. On August 4, 2025, USGS gas geochemists flew an airborne volcanic gas survey over Mount Rainier. It was the first such flight over that mountain in 27 years, which is itself a comment on how rarely this volcano has given anyone a reason to scramble an aircraft. They found no sulfur dioxide. What the instruments did detect was water vapor and carbon dioxide in amounts and proportions consistent with low-temperature hydrothermal activity. Water and old carbon, not the signature of rising magma. The conclusion drawn by the Cascades Volcano Observatory and the Pacific Northwest Seismic Network was that the swarm reflected changes in the volcano's shallow hydrothermal system rather than any movement of magma toward the surface. By the morning of August 25th, the located earthquake rate had decayed to less than one event per day, back into the noise of ordinary Rainier background seismicity. That is a clean, fast, well-executed piece of science, delivered publicly in about 4 weeks, on a question that would have taken a year to answer with the tools of a few decades ago. Everything about the response worked. Now hold that result against everything this story has established, because the reassuring headline and the actual meaning point in different directions. No magma. Confirmed. The mountain was not preparing to erupt in July 2025, and nothing suggests it is preparing to erupt now. 1,350 earthquakes generated by pressurized water forcing its way through fractures 1.5 to 4 miles beneath the summit, and a gas survey that found the summit exhaling warm water vapor and carbon dioxide. That is a direct, real-time measurement of the hydrothermal system running. That system is the clay factory. It is the thing that takes hard andesite and converts it, over centuries, into weak, saturated, slippery material sitting high on a steep slope. It is the reason the Sunset Amphitheater is streaked yellow and orange. It is the mechanism behind the Osceola collapse, behind Machiasinum Ions and Pine Beyols, behind the Round Pass mud flow, behind the Paradise and Reflection Lakes lahars, and behind whatever combination of circumstances brought the west flank down in 1507 with no eruption to explain it. It is also the most likely source of the steam explosion that may have knocked 14 million cubic yards of Little Tahoma Peak onto the Emmons Glacier in 1963. The 2025 swarm was not a countdown. It was a status report. And the status is that the process which manufactures the hazard is active right now, at depth, under the summit, moving fluid through fractured rock. So return to the open questions this story started with and close them properly. Does the next big lahar require an eruption? No. The electron mud flow settles that, and the presence of altered rock high on the west flank means the same failure mode is available today. Will the mountain give the monitoring system something to detect before it happens? Sometimes possibly. The instruments will see an eruption coming with weeks or months of warning, and they may see accelerating deformation in a failing flank if the failure happens to occur where the instruments are, and if it accelerates before it goes. They will not see a steam explosion in a hydrothermal pocket, and they will not see the last increment of weakening in a mass that has been rotting for 400 years. In the no-notice case, this case in the line, the first thing anyone learns is that a flow is already in the valley. What was the swarm telling us? That the water is hot, that it is under pressure, that it is circulating through the rock at shallow depth, and that the chemistry which removed this mountain's strength before is not a historical process. It is a current one. Monitoring at Mount Rainier has become very good at answering the question, what is this? It remains, and will likely remain, incapable of answering the question when. So assemble the whole machine one time, in order, with nothing left out. Geography sets the constraints. A stratovolcano built to 14,410 feet on a base of older, weaker rock, standing over a lowland barely above sea level, drained by 5 river systems whose valleys are steep, narrow near the mountain, and dead straight in the direction of the cities. Those valleys were graded flat by the last flows, which is why they hold the farms, the rail lines, the highways, and the schools. Chemistry removes the strength. Magmatic heat drives water through the pile. The water turns acidic, and the acid converts hard andesite into clay, invisibly, over centuries, in the high parts of the mountain where the slopes are steepest. Nobody can see it happening. The mapped concentrations of that altered rock sit high on the west flank around the Sunset Amphitheater, above the head of the Puyallup drainage, which is the valley that leads to Orting, Sumner, and Puyallup. Water supplies the force, a cubic mile of ice, plus a climate that delivers 18 inches of rain in 36 hours in November, and heat waves that drive glacial outburst floods in August. Saturation is the difference between a slope that stands and a slope that fails, and between debris that stops and debris that travels 100 kilometers. Then the flow does the rest by itself. Failure high on the mountain, transformation from avalanche to fluid within about 2 kilometers, bulking as it scrapes up ice, meltwater, riverbed gravel, and forest, confinement in the valley, keeping it deep and fast. Arrival in the lowland in tens of minutes rather than hours. Human motive supplies the exposure. Hops, coal, timber, rail, a deep water port, cheap flat land near a growing metropolitan area, a national park with a road that follows a river because there is no other way in, and more than 90,000 people who each made a reasonable decision about where to live. Technology changes what can be known, and not much else. Instruments will see an eruption coming. They will see a lahar within seconds of its birth and tell 2 operation centers, which will sound 42 sirens across 2 river valleys and push an alert to every phone in the zone. They will not see a hydrothermal steam explosion coming. They will not see the last centimeter of creep in a mass of clay that has been failing since the 16th century. They cannot make the valley longer. Distance and terrain limit rescue permanently. 32 Marines are in the South Tahoma Glacier because a crevasse on a moving glacier is not a place people can work. 11 climbers are in the Ingram because ice avalanche debris cannot be dug through before the next block falls. 6 climbers are under the Willis Wall because sending rangers there would have created 6 more bodies. In every one of those cases, the search technology of the era did its job, and the recovery was still impossible. On a flooded valley floor, after a lahar, the same rule applies at a different scale. The deposit sets like concrete. The roads are gone. The bridges are gone. And the people who would come to help arrive at the edge of a fresh plain with nothing to stand on. And history removes any argument about whether this is speculative. At least 11 large lahars have reached the Puget Lowland in the past 6,000 years. The Osceola mudflow filled the arms of Puget Sound and made the ground that Tacoma's port and the Kent Valley warehouses sit on. The electron mud flow made Orting's building lots in the late summer of 1507, without an eruption, without a storm, without any trigger that anyone has been able to identify in 500 years of subsequent geology, which leaves one temptation to refuse. Major lahars at Mount Rainier recur on the order of every 500 to 1,000 years, and the last big one was about 520 years ago. It would be easy and wrong to call the mountain overdue. Recurrence intervals are averages calculated from a small number of events. They are not schedules. The next collapse could happen in 400 years, or during the time it takes to read this sentence, and the honest position, held by the people who know the most about this volcano, is that nobody can narrow it further than that. That uncertainty is not a reason to leave the valleys, and almost nobody does. The soil is good, the commute works, the schools are decent, the ground is level, and on a clear morning the mountain fills the end of the street in a way that people who live there never entirely stop noticing. Orting has grown steadily, while its residents have practiced walking away from it. Those two facts sit side by side without contradiction, because that is how people actually live with a hazard measured in centuries. What has changed is what they know and what they have built with that knowledge. Not a wall, not a dam, not a diversion. A hazard map, a network of buried microphones and low-frequency listening posts, 42 sirens, an annual walk out of the valley by children who can recite the route, and a footbridge sized by dividing a population by a walking speed. The sirens go off at noon on the first Monday of the month. It takes a couple of minutes. In Orting, the sound comes down over the rooftops and across the fields, over a valley floor that is flat because a mountain filled it with itself in 1507, and it fades, and the traffic on the highway does not slow down. Somewhere in the school year, on one particular morning, the doors open, and the children come out in lines and start walking toward the higher ground, up the trail, onto a bridge built wide enough to pass 12,000 people in half an hour. They are practicing crossing the last mud flow before the next one arrives.